Welcome back to ECE 442-542. This is lecture 7.3b, and we're trying to wrap up our controller design. And in this short video, we will talk about the PID controller design in general and discuss how you might transition into a full-blown PID controller design based on starting with maybe a PI controller design that stabilizes your closed loop system, and that might actually provide you with a easier starting point with which to now go into this PID controller, where now we have flexibility to adjust these two different zero locations, beta 1 and beta 2. We are forced to live in a PID controller with a pole at the origin and a pole at z equal to 1. The pole at z equal to 1 gives us that integral action, which helps us with steady state accuracy. We can now track constant inputs with zero error in the steady state after the transients have disappeared. Now we need to adjust the rest of our root locus to influence our closed loop poles in this closed loop block diagram configuration, where we've now introduced a PID controller, and we can influence the shape of our root locus by the adjustment of beta 1 and beta 2, or these zero locations in our PID controller. Beta 1 and beta 2 do not have to be restricted to being on the real axis. They could actually be complex, but if you do pick beta 1 to be complex, beta 2 needs to be its conjugate. In this particular scenario, the PID controller, we now have three knobs with which we can adjust, and you could think of those as the proportional gain, the integral gain, and the derivative gain. But in this parameterization, it's easier to think about, let's just try to find good locations for beta 1 and beta 2, the two zero locations, and then adjust the gain k bar on our root locus diagram to produce the closed loop pole behavior that we want. An example that we've been using is this unstable system, where we now have g of z equaling a first order 1 over z minus 2. We have one pole at z equal to 2, and now we've seen that we can actually stabilize this controller with a pure gain controller if we adjust the gain properly. We know this is the root locus for a pure gain controller. As long as we now crank up the gain to get us beyond z equal to 1 and not so high that we go beyond z equal minus 1, as long as that one branch stays inside the unit circle, we can now stabilize that system. We may not be happy with the resulting accuracy, steady state accuracy. We may be comfortable with the exponential behavior of the response, but now what do we do? Well, now if we introduce a PI controller, which we have done for this system, now we can have the two branches meeting each other. Then they will circle around. This is the scenario, and those are supposed to re-enter at the same place. This is now our two poles to the right of 1, 0 structure that we're used to seeing. And now we could crank up the gain to get us to those triangle locations. That would be a PI controller, and that would work. But now maybe we want to pull those triangles, those closed loop poles, a little further into the unit circle. And to do that, now maybe what we can do is we can introduce another 0, but we have to, in order to keep our controller causal, we need to make sure that we have another pole in there, and a fast pole that won't influence the dynamics much is now going to be the PID controller at giving us a integrator pole at z equal to 1 and a pole at the origin. Now we can introduce a second 0, and what do we have? Now we have this real line segment is a part of our root locus. Now these may branch over and get further into the interior of our unit circle, or it may provide us with the percent overshoot behavior that we're looking for, or the time to peak behavior that we're wanting, or settling time spec. But now we've reshaped a little bit the behavior of our root locus diagram by introducing an additional pole and an additional 0. The pole is fixed at the origin. The other 0 now can be adjusted, and maybe we can slide this rightmost 0 a little to the left so that the triangles, or the closed loop poles, begin further, or actually end up further inside the unit circle. In this whole process, it may be a challenge initially to say, well, I don't even know where to begin. So just keep this note in mind. It may actually be easier to stabilize the system with some choice of maybe a 0 in a PI controller to get desired closed loop poles. Or maybe you know that this is the pattern you want, you just don't know exactly where you want those zeros to be. Well, now we can actually use MATLAB to adjust those zeros and maybe more effectively see how those changes in the 0 locations correspond to the particular structure that we want for our desired closed loop poles, or these triangles. So now we start with a stable design and then modify beta 1 and beta 2 to achieve a more desirable behavior. And we've actually, for this particular system, this system with a unstable pole at z equal to 2, we have been able to stabilize that with a PI controller, and here is the PI controller that I'm giving you as capital C sub 1 of z. We could put, obviously, the PI, the integral, that's forced on us, this z minus 1, but we found that if we put or placed a 0 at 0.9833, just a little to the left of that pole at z equal to 1, that would give us a closed loop pole z sub delta, or complex conjugate pole pair, at 0.9 plus and minus j 0.1. Now we might say, well, I don't know how to move from that to C sub 2, where now I have another pole, and I have another 0, and I have this adjustable gain k. I have 3 parameters, beta 1, beta 2, and k bar, with which I can manipulate. But now you might ask, when is it possible, or when does C sub 2, this PID controller, can we actually make it equal C sub 1 of z? And hopefully you can see that in fact we could put in a z minus 1. There's another 0 factor, and we could put in a pole here, z, and these two effectively cancel each other out, but in so doing we now have produced a PID controller that will duplicate the behavior of C sub 1 of z. Or we've now introduced, let's just assume now that this rightmost 0 factor is the z minus beta 1 factor. That one now has beta 1 equal to 0. Beta 2 is that original 0 location in our PI controller, and the k bar is the same gain value of 1.2002. That now allows us at least to have a PID controller, obviously it's somewhat benign because we have this pole zero structure, but now can we modify this a little bit? And by modify that, I'm saying, is it possible to move that 0 away from 0 and maybe move this 0 location so that we get better behavior if we're not happy with our poles at 0.9 plus and minus j 0.1 in terms of the behavior of our system at 0.9 plus and minus j 0.1. What we want to do next then is illustrate how we can use MATLAB to effectively introduce this new 0 location and modify the location of our original 0. We can't change the denominator. That's forced on us in the PID structure. But now what we want to illustrate is the fact that, if we move that 0 that we originally had that was almost at 1 to 0.9 and move our second 0 away from the origin a little bit or to the right of the origin out to z equal to 0.1, we might actually achieve better behavior, meaning less overshoot, maybe a faster settling time. That's what we want to illustrate now by using this tool in MATLAB to help us out.